Hello, welcome to lecture 31 of the course. This is lecture number 10 of module 3. In this lecture, we are going to investigate the linear response of the cavity optomechanical system around the steady state. Then we'll study the quantum limit for ground state cooling of the mechanical oscillator. So let us begin. In the last lecture, we started discussing the quantum regime of cavity optomechanical system. We assumed that the resonance frequency of the mechanical mode is much smaller than the so-called free spectral range of the cavity, which ensures that we focus on only one mode of the optical cavity. And under that assumption, we wrote down the Hamiltonian quantum optomechanical Hamiltonian for the system, and while we have written it, we just considered the optical mode and the mechanical oscillator only, and the interaction between the optical mode and the mechanical oscillator comes due to the very tiny shift of the mechanical oscillator due to optical force, and this tiny shift is assumed to be much smaller than the cavity length. And this Hamiltonian is written in a different form also, which tells us that the equilibrium position of the mechanical oscillator gets shifted from its equilibrium position 0 to a non-zero Q value when light or the light mode is present there. Then we can write this Hamiltonian in terms of the creation and annihilation operator of the mechanical oscillator as well, and we have written it in that form. After that, we work out the eigenstate and the eigenvalues of this Hamiltonian. It turns out that and it is very easy to see that when there is coupling between the light and the mechanics, the photon number gets conserved, but the phonon number is no longer conserved. In fact, we can assume the eigenstate for this system in the presence of light when Z is non-zero to be a direct product of the number state of the photon and the displaced number state of the phonons. And by solving the eigenvalue equation and taking this parameter alpha to be this, we find that the energy eigenvalue for the system can be worked out to be this one, and it tells something interesting. It tells that this extra term that is coming when there is coupling between the mechanics and the light is the energy lost by the optical oscillator due to its interaction with the mechanical oscillator, and this is basically a product of the optical force into the displacement of the mechanical oscillator from its equilibrium position. We also learned how to apply the so-called polar return transform, and by using the polar return transform, the Hamiltonian can be converted into a different form, and which tells us that the phase peak by the light mode depends on the light intensity because of the presence of this term A dagger A, which is the photon number. So an optomechanical system is inherently nonlinear due to optomechanical interaction. Till now we considered the optical mode and the mechanical mode only, but to get into a realistic scenario we have to consider the laser drive also, because the Fabry-Perot cavity is now externally driven by a laser with frequency omega L and laser amplitude omega drive. And this Hamiltonian can also be written in terms of the annihilation and creation operator of the mechanical oscillator. And as you can see that in this Hamiltonian there is explicit time dependence is there, and to get rid of this time dependence we can go over to a rotating frame of reference, and we can rewrite our Hamiltonian in this rotating frame of reference in this particular form, where this delta is the detuning parameter in terms of creation and annihilation operator. Of course you can write it in this form as well. Now, using the Heisenberg equation of motion and incorporating quantum noise, we can get the equation of motion time evolution equations for the various operators, position, momentum, and the optical mode. And here, as you can see, we have incorporated the quantum noise. This is the Langevin noise that we discussed earlier in a previous class, and gamma mp, this particular term refers to the mechanical damping. This gamma m is the mechanical damping rate, and this particular term is the noise that is entering into the optical cavity. And this noise has zero mean, as we know, because these are in nature these are Langevin noise. And also we are aware of the time correlation or the autocorrelation function in the time domain as well as the in the frequency domain. Now you please note that these quantum Langevin equations here, these are the quantum Langevin equation. These equations are nonlinear. For example, as you can see that the time evolution of the cavity mode operator A depends on the product QA here, and this is the product of two operators. So no exact analytical solutions to these quantum Langevin equations are at the moment available. So however, we can find the steady state solution in exact algebraic form, and let us do that. And to find the steady state solution for this position, momentum, and the optical mode, let us denote the steady state solution corresponding to q by q bar, and momentum variable p by p. These are q bar, p bar as a steady state solution, and corresponding to the operator A, the steady state solution is say a bar. What we are going to do, we are going to just here make the left hand side of these Langevin equations to be 0, because in steady state there has to be 0. And if we do that, then as you can see, for example, from this equation, if q dot is equal to 0, immediately we can write that p bar is equal to 0. And also from the equation of motion, time evolution equation for the momentum operator, from there we can write minus m omega m square q bar plus h cross z0 mod alpha bar square is equal to 0. You see here it would be q bar in the steady state, and a dagger a will become mod alpha square, and p in the steady state it is 0. And because we have to take the average of that, so this fluctuation, if we take the average, it is anyway going to be 0. So from this equation we can immediately write that q bar, we can write it as h cross z0 mod alpha bar square divided by m into omega m square. So this one expression we get. And from the equation of motion for the optical mode in the steady state, in the similar way we can write it. Let us look at here. From here we'll see that we can write it in the following way. Let me yes, so what we can do is this, say minus actually it is plus I delta minus kappa by 2 alpha bar. Then we have the term I z0 alpha bar q bar plus omega drive is equal to 0. And from here we can write alpha bar is equal to omega drive divided by kappa by 2 minus I into delta plus z0 q bar. This I can further write as, very simply, I will have kappa by 2 whole square plus delta plus z0 q bar whole square, and in the numerator I will have omega drive into kappa by 2 plus I into delta plus z0 q bar. Further, I can write this
in the following form. If I take kappa by 2 out in the both numerator and the denominator, I'll have here kappa by 2 and here I'll have omega drive. Let me write the denominator first. Here I'll have 1 plus delta plus Z0 q bar divided by kappa by 2 whole square, and here I have in the numerator I have 1 plus I into delta plus Z0 q bar divided by kappa by 2. If I now take say tan phi tilde is equal to delta plus Z0 q bar divided by kappa by 2, and omega drive, if I now write it as its amplitude and its phase in this form, say its phase is phi. Using this I can write alpha bar as it would be equal to omega drive. It's actually mathematical trick I'm applying here. You can do the calculation yourself. You'll have 1 plus I tan phi tilde, and here you'll have kappa by 2 1 plus tan square phi tilde e to the power I phi, and it's very simple to show that this is actually lead you to the term omega drive modulus of omega drive divided by kappa by 2, and here you'll have cos phi tilde, and this you can write it as e to the power I phi plus phi tilde. Now you can easily read out that cos phi tilde is nothing but, because you know tan phi tilde, so you can make out what is cos phi tilde would be. That would be equal to kappa by 2 divided by kappa by 2 whole square plus delta plus Z0 q bar whole to the power half. Okay, now using this we can write alpha bar as equal to omega drive modulus of omega drive divided by kappa by 2 whole square plus delta plus Z0 q bar whole square to the power half, and here you will have e to the power I phi plus phi tilde. Now if we choose the phase of the drive such that phase of the drive phi such that it is equal to minus phi tilde, which is actually equal to minus tan inverse of delta plus Z0 q bar divided by kappa by 2, then alpha would be a real quantity, and alpha bar we can write as omega drive divided by delta plus Z0 q bar whole square plus kappa by 2 whole square to the power half. So in this case alpha bar is now a real quantity, and also you see the number of intracavity photon is given by alpha bar square.
Now we will investigate the linear response of the optomechanical Fabry-Pérot around the steady state values, which already we have found out, and this is going to be a semi-classical approximation
where we will write each dynamical variable. For example, this optical mode, which is a dynamical variable, and the mechanical oscillator variables, the position of the mechanical oscillator and its momentum, these are the dynamical variable, and we are going to write it as a sum of two parts. One is the classical part, that is the steady state value. For example, for the optical mode, we can write A is equal to alpha bar plus its deviation, the time dependent quantum fluctuation part, and the position operator of the mechanical oscillator, its steady state value is q bar, and its the corresponding quantum fluctuation is delta q. And for the momentum of the mechanical oscillator, its steady state value is p bar, and the corresponding fluctuation, quantum fluctuation, is delta p. And this delta a, delta q, and delta p, they have zero mean quantum fluctuation. And then if we insert these quantities in our quantum Langevin equation, let me write it again. Q dot is equal to p by m. All these are operators, so sometime I may not write it, but you please understand that I am now talking about quantum operators here. We have m omega m square q plus h cross z0 a dagger a minus gamma, this is gamma m, it is gamma m p, and the Langevin noise xi. And we have q dot is equal to, in fact q dot I have written already. We have a dot is equal to I delta minus kappa by 2 a I z0 q into a plus omega drive and the quantum noise, that is square root of kappa a in. Now if we put this answers in this quantum Langevin equation, then we can write, you can easily show it. You will get delta q dot is equal to delta p by m, then all these are operators again, and we have delta p dot is equal to minus m omega m square delta q plus h cross z0. And I will urge you to verify it. It's very simple, or otherwise maybe we can straight away show it in our problem solving session as well, but it's very straightforward. It is delta a dagger delta a, and we have minus gamma m delta p plus xi. And for the optical mode, the fluctuation is delta a dot is equal to I delta plus the detuning parameter plus z0 q bar minus kappa by 2 delta a, and I have I z0 alpha bar plus delta a delta q minus square root of kappa, will have a in here. Now you see, since these fluctuations are assumed to be small, we are going to retain only those terms which are linear in the fluctuation. So if we go to retain only the linear terms, and then the terms which are bilinear, for example delta a dagger delta a, this is a bilinear term, and the product of delta a delta q which you are going to encounter here, for example delta a delta q, these we have to remove because these would be very further small, and we will just concentrate into the linear terms only. Then this is going to simplify our these Langevin equations corresponding to this fluctuation. Then we can write delta q dot. So let me first write that what we are ignoring. We are ignoring here ignoring the nonlinear terms, and that is why we are saying we are doing the linearization, ignoring the nonlinear terms, we get delta q dot is equal to delta p by m, then delta, all these are again operators, delta p dot is equal to minus m omega m square delta q plus h cross z delta a plus delta a dagger minus gamma m delta p plus xi, and we have here delta a dot is equal to I delta dash. This is the modified detuning parameter or effective detuning parameter that I'm going to define soon, minus kappa by 2 delta a plus Iz delta q minus square root of kappa a in. Now here this parameter z is equal to z0 into alpha bar, and this particular parameter z is termed as the linearized optomechanical coupling. It is called linearized optomechanical coupling for obvious reason. It is also sometimes called multiphoton optomechanical coupling, because in the steady state coupling, for example z0, this is enhanced by the steady state photon number ns, because alpha bar, you see, this is actually square root of the steady state photon number, because mod alpha bar square gives the intensity, and that is equal to the number of photons in the cavity in the steady state. So therefore you see that your z0 is now getting enhanced by the amount by alpha bar, and that's the reason this parameter z is called also as the multiphoton optomechanical coupling. And this quantity delta dash, which is the effective detuning, this is called effective detuning, and this is delta dash is equal to delta plus z0 into q bar. So this set of equations actually constitute the linearized quantum Langevin equations for the optomechanical Fabry-Perot cavity, and it contains the full linear response of the system. In fact, this set of equations could be derived entirely in terms of creation and annihilation operators as well, and to do that we are going to start with the Hamiltonian, where we write the whole Hamiltonian in terms of only creation and annihilation operator in this form: minus h cross delta a dagger a plus h cross omega m b dagger b minus h cross z a dagger a into b plus b dagger plus I h cross omega. This actually we have written earlier also, so hope you are getting it. It is a dagger minus a. This is written exclusively in terms of creation and annihilation operators for the optical mode as well as the mechanical mode, and from here we can as usual get the Heisenberg equation of motion for the optical mode and the mechanical mode, a dot and b dot, and you will get it as, say, I for the optical mode you will have I delta a plus I z a b plus b dagger plus omega drive minus actually we have written it earlier, minus kappa by 2 minus square root of kappa a in, and for the mechanical mode you will have minus I omega m b plus I z a dagger a minus gamma m by 2 b minus square root of gamma m b in. Now here this is the quantum noise that is entering into the mechanical mode, mechanical substrate or the mechanical oscillator. This is the damping of the mechanical damping. Now if we want to linearize it, so we can do that exactly by the same procedure that we have already adopted. Here a will write this annihilation operator For the optical mode, we'll write it as two parts, that is the steady state value and its deviation from the steady state value, that is the quantum fluctuation part. And for the mechanical mode also, annihilation operator would be its steady state value plus delta B. Okay, so similar calculations we can actually carry out here also, and this will lead us to these equations for delta A and delta B. For delta A, it will be delta A dot is equal to I delta dash minus kappa by 2 delta A plus I Z delta B plus delta B dagger minus square root of kappa A in. And for here, by the way, delta dash is equal to the effective detuning here would be delta plus Z into beta plus beta star, and Z is equal to, that is the linearized optomechanical coupling here would be Z plus alpha bar, and delta B dot is equal to minus I omega m. I request you to please do this yourself and please verify it whether I'm writing it correctly here. You have delta B plus IZ delta B plus delta B dagger minus square root of gamma m B in. The Hamiltonian corresponding to this linearized regime can be written in this form, that is H is equal to, now we are going to term it as the linearized Hamiltonian, or rather we'll simply write it as a simple H, but you understand that now I'm talking about linearized Hamiltonian. That would be minus H cross delta dash delta A dagger delta A plus H cross omega m delta B dagger delta B minus H cross Z delta A plus delta A dagger into delta B plus delta B dagger. So this is the linearized Hamiltonian in the absence of damping and other quantum noise, and you can verify whether this Hamiltonian that I have written is correct or not just by applying the Heisenberg equation of motion to get back these equations, time evolution equation for the operator delta A and delta B in the absence of the corresponding dampings and the quantum noise. Okay, in fact, in many cases or many a times people prefer to write delta A as simply A and delta B as B, with the understanding that they represents the quantum fluctuations. So if we do that, then we can rewrite this linearized Hamiltonian as H is equal to minus H cross delta dash A dagger A plus H cross omega m B dagger B minus H cross Z A plus A dagger into B plus B dagger, and here delta dash is equal to delta plus the optomechanical coupling constant, linearized optomechanical coupling constant Z into beta plus beta star. And here let me remind you that this Z is related to the capital Z, and this is the alpha bar. What we are going to do that this particular part is generally not that very great, so now onwards in the rest of our treatment we are going to take delta dash to be nearly equal to delta, and where you know that delta, this detuning parameter, is omega L minus omega 0, where omega 0 is the resonance frequency of the optical cavity. The physics described by this linearized Hamiltonian can be depicted schematically, and let me show you, because in essence what we are having is we are having two harmonic oscillator. One oscillator is due to the optical cavity, and this is represented by the operator A, and this oscillator has oscillation frequency minus delta, as you can see from here, and other oscillator is the mechanical oscillator, and this is represented by the operator B, and it has oscillation frequency omega m, and these two oscillators are coupled via this optomechanical coupling, and this described by this coupling constant. Their coupling is described by this optomechanical linearized optomechanical coupling constant Z. Also, you see that this mechanical oscillator, it has a damping, and it damps at the rate of gamma m. And actually what happens is that the quanta of these mechanical oscillators are called phonons, and these phonons get decayed to some kind of a substrate or some bath. So we can term them as mechanical bath, and they are at some finite temperature. Okay, so they get decayed to this mechanical bath. Also, the photons also has a dissipation constant, as you know, that this decay at the rate kappa, and they decay into the environment, which is described by the so-called electromagnetic vacuum. So this is electromagnetic vacuum, and this electromagnetic vacuum is modeled as harmonic oscillator, and they oscillate at optical frequency, and because of that electromagnetic vacuum is effectively at a temperature T is equal to 0. So we have a situation that when this delta is less than 0, that means in that case minus delta would be greater than 0, and we are going to have a positive optical oscillator, and the mechanical oscillator is oscillating at frequency omega m, and it is, as you know, it is already connected to a mechanical bath at finite temperature. So effectively speaking, the mechanical oscillator is a hot oscillator and the optical oscillator is a cold oscillator. So this would effectively bring down the temperature of the mechanical oscillator due to its coupling to the optical oscillator. Now this is basically, in a very simple way, the principle behind from this pictorial diagram. It is clear that this is how the mechanical oscillator gets cooled due to its coupling to the optical oscillator. When delta is less than 0, it implies that omega L is less than omega 0, and it physically means that the laser is rate detuned, and we are going to discuss considering the laser to be rate detuned, and because now we can achieve what is called ground state cooling of mechanical oscillator. But because of quantum physics, we will see that there is a limit to this cooling. So we are now going to discuss quantum limit of ground state cooling of mechanical oscillator. Before I go on to discuss the quantum limit for ground state cooling of mechanical oscillator, let me remind you why achieving ground state is of paramount importance. It is important if we want to study quantum phenomena in macroscopic objects. As you know, the mechanical systems can be treated as harmonic oscillator, and the adjacent energy levels of these harmonic oscillators are equally spaced. And if we want to study the quantum feature of this massive mechanical system or mechanical oscillators, then the discreteness of the energy levels has to be there, and it will be there provided the energy due to the thermal fluctuation, which is kBt, is much smaller than the energy spacing, that is h cross omega m, that already we know. So this is extremely important, and this is why we need to cool the mechanical oscillator to a very low temperature. In terms of phonon picture, this actually says that it amounts to saying that the number of phonons or the average number of phonons has to be very small, we can get achieve the ground state provided the average number of phonons is too small. However, as we'll see that because of quantum mechanics, it is not possible to lower the average number of photons arbitrarily. And now the question is, what happens if the mechanical oscillator gets coupled to an optical cavity? Say the mechanical oscillator is in one photon state. Let us say this is our one photon state, this is the ground state, this is the two photon state, this is the three photon states, and so on. Then if it is now coupled to an optical oscillator or an optical cavity, then the mechanical oscillator, which is, we are assuming it to be in the one phonon state, it may go to the ground state at a transition rate, say gamma down due to the coupling with the optical oscillator. On the other hand, if the oscillator is already in the ground state, that is represented by this gate 0 here, if it is already in the ground state, then there is a very small probability that it derives some energy from the optical cavity and transit to the one phonon state with a rate at a rate, let us say gamma up. For cooling, it is obvious that the downward transition, that is gamma down, has to be greater than the upward transition rate.
Now, in general, if a quantum system is coupled to some environment, the interaction Hamiltonian is given by in this form. So, say the system operator is represented by A and the fluctuating environment is represented by the operator F. Here A is the system operator and F is the fluctuating operator belonging to the environment. Here I am considering a general case, and then we will apply this case after we discuss it. We will apply it to our specific case. To give you an idea, you know that when an atom and an electric field interacts, the interaction Hamiltonian is given by minus mu dot E. Mu dot is the dipole moment operator. Suppose we are considering a two-level atom, then mu dot is the, say, dipole moment operator, and E is the electric field operator. So this is the interaction Hamiltonian. So similar way, we can talk about the general case in this form. Now the transition rate within the system. So we have this system A, and the fluctuating environment is represented by this F. So they are getting coupled to each other, and that's why we are having this interaction Hamiltonian here. And within the system, suppose we want to know, say, how the system is transiting from some initial state I to some, say, final state F, then this transition rate is given by the so-called Fermi golden rule, and this rate is represented by, say, gamma I to F, or simply I can write it as gamma Fi is equal to, as per the Fermi golden rule, it is, we are going from the initial state in the system to the final state F. So this is the matrix element. This is the probability of going from the initial state I to the final state F within the system. So mod square will give you the probability. Then we have 1 by h cross square, and we have to calculate this spectrum of the fluctuating operator at the frequency that I'm going to write it as omega, which represents the energy difference from the initial energy state of the system to the final energy state of the system divided by h cross. So this is the formula. This is known as the Fermi golden rule, and this formula is applicable when the interaction between the system and the environment is weak.
So okay, by the way, you recall that this spectrum omega SFF omega is, if you remember, that this is nothing but the Fourier transform of the correlator of this operator f. So this is the Fourier transformation you have to calculate, and we'll see how to do that for our specific case. Now in our case, we have our interaction Hamiltonian to be like this. This is equal to minus h cross z into b plus b dagger into a plus a dagger. All of them, these are quantum operators, because you remember we have replaced delta A, that is the quantum fluctuation belonging to the optical cavity, we replaced it by A, and similarly the quantum fluctuation belonging to the mechanical system is represented by this, simply replaced by B. And here we have this our system, this part is the system, and we can take it as our environment. We can say that our mechanical oscillator is surrounding by optical cavity, which is here acting as the environment. Now using the Fermi golden rule, we can write the rate, for example, if we are going from the one phonon state in the system to the zero phonon state, that is and the system operator, let me write it as h cross z b plus b dagger, and this is the matrix element. We have to take the mod square and 1 by h cross square, and here we are going from the initial state to the final state, so upper state to the lower state, so this would be the downward transition. So let us say it is gamma minus, and we have this fluctuating environment represented by a plus a dagger. So for the moment, let me just write f here, and we have to calculate SFF, and at frequency initial, we are going from the higher energy state, one phonon state, to the zero phonon state. So therefore this would be simply the mechanical frequency of the our system or the oscillator. We have to evaluate omega at capital omega m, right? So you see, this part is easy to calculate, because we know that when this annihilation operator operates on the one phonon state, we will get simply 0, and therefore because of this you can immediately see that this downward transition rate, from here I will get the term z square, and we have of course only z square, because h cross square will get cancelled out, so we'll have z square, and we have to calculate the spectrum at the oscillation frequency of the mechanical oscillator. Let us calculate it. So here SFF at omega is equal to capital omega m is equal to the Fourier transformation of the term a plus a dagger, it is at time t, and a plus a dagger at time t is equal to 0. We have to calculate it, and finally all the calculations has to be carried out at omega is equal to capital omega m. Now you note that this already, as I said, that this operator A is the quantum fluctuation corresponding to the optical mode, and it is basically in the ground state. So we have to calculate the expectation value of this particular term here, a plus a dagger at time t and a plus a dagger at time t is equal to 0. This we have to calculate with respect to the ground state, because it is already in the optical oscillator is in the ground state, because effectively it is at temperature 0, as you know, because the optical frequency is in the around 10 to the power 15 hertz or so. So that's the reason we can calculate it in the ground state. Now if we break it, okay, we will do this first. If we break it, we'll get 4 terms, and most of the terms will vanish, except all terms will vanish except as you will see that only term that will remain non-zero would be a of t and a dagger of 0. This would remain this will remain non-zero, but rest of the terms will 0. Let me show how. Actually, it's very trivial to see. For example, you have a dagger t and a of 0, and because you are calculating it in the ground state, so therefore you can immediately see that when this annihilation operator operates on the ground state, you are going to get 0. Similar way, you will have a dagger t, a dagger of 0, that is also going to give you 0. And then also you will you can see that you will have also a of t, a of 0 would be equal to 0, right? So only term that would remain non-zero would be this one. So we have to calculate this as, so we'll be left out with only one term, and we have to calculate the Fourier transformation of a dagger of t, sorry, this would be a of t, it would be a of t, a dagger of 0 and dt, evaluating at omega m. Let us do it. But before we do that, first we have to express this quantity, express a of t in terms of a of 0, and that we can do because we know the quantum Langevin equation for the optical oscillator. So that is a dot is equal to, in the absence of mechanics, I can write it as minus I delta kappa by 2 a minus square root of kappa a in, and the solution is trivial, and that is a of t would be equal to a of 0 e to the power I delta t minus kappa by 2 t, and there would be terms belonging to the 0 point fluctuation because of this. But as you will see that if we take the average, then this fluctuation part is going to vanish, and this we have written for t greater than 0. And so therefore what we'll have is this spectrum would be minus infinity to plus infinity dt e to the power I, from the Fourier part we have I omega, and now here delta is there, omega plus delta t minus kappa by 2 mod t, a of 0, a dagger of 0. Now here I am taken mod t because I have taken from the t less than 0 also is taken into account because the integration is from minus infinity to plus infinity. So that's the reason we have put a mod sign here to take into both the cases. So let us now work it out. One thing you can immediately see that this quantity is simply equal to 1, right? Because it is trivial to see. Okay, let me just show you. We have a dagger 0, so you will get, because of this you will get 1, and because of this when it operates on the bra part you will get 1, and that is equal to simply 1. So we are left only to evaluate this very simple integration. It is dt e to the power I omega plus delta t minus kappa by 2 mod t. In fact, you see that this I can evaluate it very simply. Let me do it here. I can take the integration from 0 to infinity, then I have to bother about the real part. So you can see you have 2 into real part dt e to the power I omega plus delta t minus kappa by 2 t, that I can write. And if I evaluate this integral, simple algebra actually, and you will get it as kappa divided by omega plus delta square plus kappa by 2 whole square. Therefore, the transition rate, downward transition rate, remember we have to evaluate it at capital omega m. So therefore, I will have z square into kappa divided by omega m plus delta whole square plus kappa by 2 whole square. Exactly in the similar way, we can calculate the upward transition rate gamma up, and that would be equal to z square into kappa divided by omega m minus delta whole square plus kappa by 2 whole square. Now in this case we have evaluated the spectrum at the frequency minus omega m, because here we are going from the 0 phonon state to the 1 phonon state. We can now plot the fluctuation spectrum as a function of frequency for delta less than 0, because we are interested in cooling. As you can see that this spectrum is Lorentzian and it has a maximum at minus delta, and the width is given by the cavity decay rate kappa. And if we want to obtain the downward transition rate, as we have already seen, that we have to evaluate the spectrum at frequency omega is equal to plus omega m. Let us say we are interested in calculating the downward transition rate, then we have to evaluate it omega m. So from here this distance in frequency is omega m, and this will give us the downward transition rate. On the other hand, the upward transition rate can be obtained if the spectrum is evaluated at the other end, that is at frequency minus omega m. So this would be somewhere lying here in distance in frequency unit. So this would be minus omega m. So this is our gamma up. It is clear that from this plot as well that the downward transition rate is higher than the upward transition rate. Let us now calculate the phonon numbers to which our mechanical oscillator settles down to. The idea is to calculate the average phonon number and see if we can somehow suppress the phonon numbers to 0 by optimizing the parameters of the optomechanical system, achieving a pure ground state. But firstly, let us find out what is the phonon number in the steady state. In the steady state, the net flow of phonons from the upward state to the downward state. Let me write here, net flow of phonons from up state to down state must be balanced by net flow of phonons from down state to up state. Then we will achieve the steady state. And in terms of probabilities, we can write it as, say we are in the ground state, that is the probability of being in the ground state is say P0. We are having in the ground state and corresponding probability is P0, and we go from the ground state to the up state, and up state probability, occupation probability is P1, and this is the 1 phonon state, and so on. We have other state, but we are confining our discussion to the 1 phonon state and the ground state only. So it would be P0, the net flow of phonons from the up state to the down state would be P0 gamma up, and it has to be balanced by, now we are in the up state, that is P1, and the rate of transition in the downward is given by gamma down. You can write down the ratio of this upward transition and the downward transition as P1 divided by P0, as is evident from this expression. Now invoking the Boltzmann distribution for probabilities, P1 by P0 is equal to e to the power minus the energy difference between these two energy levels, and that would be h cross omega m divided by kBt. And from here we can immediately write that the ratio between the transition rate for the upward and the downward is equal to e to the power minus h cross omega m by kBt. Again, we know what is the upward transition rate and the downward transition rate. Already we have derived the corresponding expressions for them. So if we put those terms here, and we'll get this ratio as delta plus omega m whole square plus kappa by 2 whole square divided by delta minus omega m whole square plus kappa by 2 whole square. Also, we know that the average number of phonons is given by this expression, that is 1 divided by e to the power h cross omega m by kBt minus 1, and from here we can quickly write that e to the power minus h cross omega m by kBt is equal to n bar divided by n bar plus 1. So we then can write that this ratio n bar divided by n bar plus 1 is equal to delta plus omega m whole square plus kappa by 2 whole square. I'm just repeating here, and we have delta minus omega m whole square plus kappa by 2 whole square. Okay, so now let us optimize the parameters, because our goal is to minimize the average number of phonons. So we have to minimize n bar. To do that, we have to minimize the ratio. So this implies that we have to minimize this ratio of gamma up and gamma down, this ratio of gamma up by gamma down. That means we have to concentrate on this expression, or then you will see that I can then write, if I invoke the resolved sideband regime, if we work in the resolved sideband regime, then I can write n bar by n bar plus 1. By the way, resolved sideband regime, we have in that regime our kappa has to be much smaller than the resonance frequency of the mechanical oscillator, and also we are going to take delta is equal to minus omega m, and if I take that, I can write this expression as kappa by 2 whole square divided by 4 omega m square. As you can see, I have just put delta is equal to minus omega m here, and then here I have kappa by 2 whole square, and we can write this as n bar plus 1 divided by n bar is equal to invoking the resolved sideband regime. That means I can ignore this term, and then I have here it will be 4 omega m square divided by kappa by 2 whole square, and therefore from here you see that the optimized, that means the minimum number of average number of phonons would turn out to be the ratio of kappa by omega m. So this is the expression we are going to have. Now clearly, if we want to have the phonon number to be much less than 1, to get n bar to be much smaller than 1, so that we can get the ground state of the mechanical oscillator, we need to make kappa has to be very small. Lower the kappa or the cavity rate, better is the probability that we will reach into the ground state of the mechanical oscillator. And lower kappa cavity decay rate means that we need to have a very high Q cavity.
Let me stop here for today. In this lecture, we have studied the linear response of the cavity optomechanical system around its steady state, and which led us to the regime of linearized cavity quantum optomechanics. Then we also studied the quantum limit for the ground state cooling of the mechanical oscillator. In the next lecture, we are going to study various other phenomena related to cavity quantum optomechanics, such as squeezing and normal mode splitting and so on. So see you in the next lecture. Thank you.